Good day, ladies and gentlemen, and ladies. Welcome back to the EBN tutorial videos. So in this video, we are going to be covering chapter 3. In chapter 3, you get introduced to the basis of electronics, the core. You start with mesh analysis and nodal analysis, for everybody who's doing electrical, and computer engineering. If you don't understand this chapter, then may the Lord be with you, because literally, this is electronic engineering, this is electrical engineering, and computer engineering is mostly about programming, but also it's bundled into that, the 3 EEC, the boss engineering, shout out to all them, you know what I'm saying. So if you understand this one chapter, you understand electronic engineering, the EEC of engineering. So pay attention, because this is like those life-changing chapters, And you know how we do it. First video covers theory, and then when you're done with the video, you're just like, what did he just say? Then the next video, a bunch of examples, one after the other, after the other, after the other, after the other, after the other. Then you're like, oh, I finally get it. Yeah, so rambling on for a little bit. Okay, so this one is nodal analysis. So with nodal analysis, so you choose your nodes, right? Let me see if I've got for here, right? There's a good one. So you select a node as your reference node. Your reference node is basically your ground node. You see this guy, that sign means that's your reference node. That means this node is equal to 0 volts, right? That's what the reference node is. So you first select your reference node, and then you assign voltages V1, V2, V blah 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 according to the nodes. You see, here is a node right there, so that's why this one's called V1, right? Going to a different color like gray, here is a node, as you can see, V3. Going to more different color, blue. Here is a node, as you can see, that's V2. Yes, so that's that step about assigning voltages V1, V2 till Vn to your nodes. It doesn't really matter which order you assign the voltages, but in the test, because you're still in first year, they want to assign you the nodes. They want to tell you this node is V1, that node is V2, blah 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 blah. You know what I'm saying? And then you do KCL at the nodes. So basically, you can see all of these arrows: currents, currents. So the one thing about this is that some people, how do you begin assigning which way the current is going to be flowing? So first of all, by now, you should realize that current flows from the negative to the positive voltage from your voltage source, right? So your initial current is going this way. That is step number 1. Determine the initial current, I.O. Stylus is still trying to fight me. Why, Stylus, right? Why you gotta be on your... Is it that? No, I can't say that. That's your I0, right? So this is your initial current that is coming from your voltage source, or sometimes it's coming from your current source. So now that you know the direction of the initial current, you know that current is going to speed up this way and it's going to speed up this way, right? And then you follow those arrows, right? This arrow is going this way, so therefore there's going to be a current going this way. And this way is going to keep on going like this, then it's going to speed up this way, then it's going to speed up this way, right? For now, don't worry about this funny business going on here. Actually, no, it doesn't really matter. because this current is coming this way. All of this current here. Let me draw it in a different color. Red. No. Okay. So this current I2, because you've got a voltage source here, you cannot force current to go through this way. So therefore, this current that's going here, okay, purple. I like purple. So this current that's going this way, that is created by this 5-volt source, comes and meets here, and then bam, this current I1 combines with this purple current to make I2. Like, this is just, like, this is something that you'll get after doing a bunch of examples and, such and suches. Because, yeah, you'll just get used to it. This is something that you get out of practice. You practice, do a bunch of problems, get a bunch of them wrong, and then you have that aha moment where that light bulb goes on, you know what I'm saying? So, yeah. That's the KCL that's being applied to the n-1 non-reference nodes. Use Ohm's law to express the branches in terms of node voltages, and then now you've got a bunch of simultaneous equations and you solve them. Sometimes you solve them using Cramer's rule, or sometimes you get out your calculator, your Casio FX991ZA+, right? So the way you do it, you press mode. Mode is right next to setup, right by the on button, and then you choose is it equation, option 5, EQN, right? So then you choose either option 1 if you've got 2 equations, or you choose option 2 if you've got 3 equations. Then you just type in all of your numbers, and then you get your answers. Because at the end of the day, in EBN, only your final answer matters. They do not care about you working out. So yes, use the power of a good calculator. Get yourself the it's silver and blue calculator. That one is boss. It's 100%. Also, the previous version is pretty cool, but like that previous version doesn't have complex numbers, doesn't have factorial. Maybe it has factorial, I don't know. But obviously, like, stay up to date with the current trends and get yourself a Casio excuse me, a Casio FX991ZA+. Yeah. And then the one thing about your KCL is that your current flows from a higher to a low potential of the resistor, and also you basically write the current in terms of that thingy there. And these, all that I'm saying, all this gibberish, yabba 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 hoo hoo ha ha, will make sense once we bash through a couple of examples, which will be done in the second video. Right now, we're just trying to go through the theory, we're just trying to see some stuff, and hopefully you are in class for at least like one of these lectures. Because like if you like totally missed it, like, then I suggest that you like do every single one of the problems at the back of the book, because as I said, this is the most this chapter is like the most important chapter of EEC engineering. Like, ooh, this is when like everything goes in. If this chapter does not make sense to you, please, I beg you, please make an appointment with me, or with another tutor, or with a friend, so that somebody can explain to you. Because if you do not understand this chapter, you will fail electrical, and computer engineering. Like, it's that deep. This is a deep chapter. This is like one of those chapters. Oh yeah, let's erase these strokes. Erase. So sometimes you get what is called a supernode. A supernode is when you have a voltage source right between two different nodes. So with your supernode, you need to, what did you do this? Well, with your supernode, you have an extra equation here that basically says V2 minus V3 is equal to 5 volts. That's basically what your supernode does. And then you've got an extra equation. That's what supernode is all about. And then you consider this supernode as being one node, right? So then when you do your KCL here, and then you combine it with this KCL that's happening here, and here, right? As I said, we will do the examples, supernodes, supermeshes, and all those fun things, because I really enjoy this chapter, because this is engineering. This is the good stuff. This is the stuff that I live for. Okay. And then there's mesh analysis. Mesh analysis is so easy, like so easy. Nodal analysis is like a little bit more difficult than mesh analysis, but mesh analysis is like so easy. So mesh analysis, you assign mesh currents I1, I2, I3 till IN. So first of all, the one thing that some people always, it always bugs them, is that your direction is clockwise. This is something that you just accept. Your mesh currents are going to be clockwise. That's just the rule. That's what happens, right? That's just the rule. And then you apply your KVL to each of the n meshes. So your KVL basically V is equal to Ri. So then here you'd get for mesh 1, for example, you'd get what is it? Just for the KVL here would be 6I1 type of thing, But like as I said, we will go through more theory. We'll go through more examples. For right now, we are looking at theory. Okay. So then yes, that's that, and then you solve the simultaneous equations. And then you get your supermesh. Your supermesh is when you've got when you've got a source, a current source that is between two meshes, and then you consider this mesh and that mesh to be one mesh, and then you just say that I2 minus I1 is equal to 6. Why I2 minus I1? Because this one enters this way, and that one is minusing to give you the 6. Yes. That is that. And then we get to our transistors. Transistors are super dope. Transistors are the basis of like most electronics, because transistors they make amplifiers, and amplifiers can make a low signal become big. Let's say, for example, you're looking into the depth of space for alien life, and then you get this little chirp, that little chirp can be amplified. Okay, that's a really bad representation for what a signal is. This little signal can be amplified to become a bigger signal so that it can, be processed and everything, and then you just, it's awesome. It's an awesome little thing. But I know right now they are going to make you hate it, because they really teach it in a very crappy way. So then right now you guys are looking at BJTs. I did a module in 4th year where we look at like, I think about 6, 7, 8 different types of transistors. So, but for now, you're going to only look at BJTs. When it comes to BJTs, there's an NPN and there's a PNP. You look at it by the way this arrow is pointing. NPN is going down, going towards the emitter. That's your NPN. Your PNP is going into the emitter. Yeah, I really enjoy this chapter. Okay, so don't judge me. Okay, NPN, PNP, and then these equations, these are just equations you have to memorize, and memorize. Yeah, so that's that. But I am going to teach you a super dope, super neat, a couple of more super cool equations. So let me just redraw a NPN, right? So then we're gonna call this V input, as in the input current. We're gonna call this guy RB, the resistors as the base, and then you've got your RE, which is your emitter that's being grounded, and then you've got your RC. This is RC, and then this is your power, VCC. Well, this is how we were taught how to draw it in ENE 410, my fourth year module, where all we did was just the transistors. So when you see it, just always remember it like this, right? So number one of the most important things that is not clearly stated all the time is that there's a voltage drop here from here to here of 0.7 volts. Why 0.7 volts? Should I really explain it to you when it doesn't really matter? It doesn't really matter at this moment. Just know that there's a voltage drop. Think of it this way. There's the physics. For it to turn on, you need a 0.7 voltage difference for it to turn on. So therefore there's going to be a voltage drop. Like it's very deep, and like it's not going to be tested, so I don't want to waste your time trying to explain this, right? So this is obviously the collector. So I'm going to draw in a couple of voltages. I just say bear with me for now with with the equations I'm gonna write down, because these equations you will see where they are applied in the examples. I mean in the example video that's gonna follow up. So yeah, for now I'm just gonna write these down. So this is V of CE, the difference between the collector and the emitter, and this is V of BE, the difference between the base and the emitter, right? So V of BE at your level, just always make the assumption that it's 0.7. When you get to higher levels of electrical, and computer, you are going to find out that V of BE can actually change, become lower, become higher, depending on the type of transistor you're working with. And yeah, right now I'm going to jot down 5 equations. I just say write down these 5 equations and memorize them, because in the next video I'm going to be also using these 5 equations when we're doing the examples. So here we go. We say that I of C is equal to V of input minus V of BE divided by R of C. And I of B is equal to V of input. Oh wait, no, that is incorrect. I knew it looked weird. I of C is VCC minus V of... Oh yeah, that is right. Okay, so I of B, yeah, this one is I of B. I of B is equal to V of N minus V of BE. Yeah, I knew it. Okay, I apologize for writing these down, because I'm looking down in my 4th year book, and sometimes I scribble instead of writing like a proper person. So I of C is equal to VCC minus VCE over R of C. So the current going through here, right, is equal to V of CC, which is the power. Okay, the way you probably know V of CC will be like plus minus with an earth, right? That's what V of C is. It's your power. And minus V of CE, the voltage difference here, divided by R of C, the collector resistor. Okay, And then you've got I of B, the current in your base, which is here, I of B, I of B, that is equal to V of I, your input, minus V of BE, which is your 0.7 volts, right? And then you divide by R of B, your base resistor, plus 1 plus beta R of E. That's what I of B is equal to, okay? And then you've got V of CE is equal to VCC minus RCIC minus REIE. I mean, that one is pretty intuitive, right? So the voltage V of CE is equal to the voltage going on here, which is this guy, minus the voltage going on there, which is that guy. Basically, right? The voltage there minus the voltage there, that's equal to the voltage in the middle. And so to further simplify this formula, you can say that this is equal to VCC minus IC into RC plus beta plus 1 over beta RE, right? Because most of the time you may have IC and sometimes you have IE, right? But if you only have IE, you can use this version,